Hello, and welcome to this video on multi-engine aerodynamics. Up to this point in flight training, most pilots have only flown single-engine airplanes. Now you take a bold step in your aviation career with the addition of a multi-engine airplane to your capabilities. For many pilots, flying a multi-engine airplane is an exhilarating yet challenging experience. To take full advantage of the airplane's capabilities, performance, and safety, you must be well-trained, knowledgeable, and proficient in every aspect of its operations. A major difference between flying a light twin airplane and a single-engine airplane is knowing how to manage the aircraft if one engine loses power. But before we delve further into that, let us review some fundamental concepts. Let's begin with the four forces acting on an aircraft. These are thrust, drag, lift, and weight. Thrust is the forward force produced by the propeller and opposes drag. Drag is the rearward force caused by airflow being disrupted over the wing that opposes thrust. Lift is the dynamic effect of air acting on an airfoil. It acts perpendicular to the airplane's flight path through the center of lift. During level flight, lift acts opposite to weight. Finally, weight is the total load of the aircraft and acts downward because of gravity. It acts opposite to lift through the center of gravity. Now that we have reviewed four forces acting on an airplane, let's look at how they differ on multi-engine and single-engine airplanes. Thrust. On single-engine airplanes, thrust acts right down the longitudinal axis of the airplane due to the position of the engine. This is also known as centerline thrust. On the other hand, the thrust on most multi-engines does not act down the longitudinal axis due to the engines being mounted on the wings. Instead, thrust is acting on both sides of the fuselage if both engines are producing the same thrust. Furthermore, the amount of thrust produced is more because there are two engines as opposed to one. This typically results in higher airspeeds during takeoff, landing, and cruise. Lift. The power plant is mounted to the front of a single-engine aircraft. On most light twin engines, the power plant is mounted on the wings. This results in induced airflow over the wings. Induced airflow is air from the prop wash and causes increased lift production. The added lift is beneficial since most light twin engines tend to be heavier than single-engine aircraft. Drag. Both induced and parasitic drag are present. Since multi-engine airplanes tend to create more lift on the wings, they may have winglets to help reduce induced drag. Weight. Most multi-engine airplanes are heavier than the Cessna 172. They, therefore, need to create more lift to overcome the extra weight. This results in major performance differences, such as stall speed. Now that we have compared the four forces acting on a single-engine and multi-engine aircraft, let's look at another significant aerodynamic factor: left turning tendencies. On single-engine airplanes, predominant factors contributing to left turning tendencies include P-factor, torque, and spiraling slipstream. These same factors affect multi-engine aircraft as well, and the resulting effect is significantly greater because there are two engines. If the multi-engine has propellers that rotate in the same direction, P-factor, torque, and spiraling slipstream amplify the left-turning tendencies. These type of multi-engine aircraft are commonly called conventional twins. The amount of right rudder required to maintain coordination in flight is also greater than with a single-engine aircraft. On the other hand, if the propellers spin opposite to each other, that is, clockwise and counterclockwise, the turning tendencies are minimized. These multi-engines are commonly called counter-rotating twins. We have reviewed the four forces acting on an aircraft and compared the aerodynamic forces acting on a single-engine aircraft to a multi-engine aircraft. Remember that the forces remain the same but are larger in multi-engine aircraft. Now, we will continue to explore how to safely and effectively operate a multi-engine airplane when one engine becomes inoperative. Let's begin by briefly discussing a few one-engine inoperative terms and principles. VXSE, best angle of climb with one engine inoperative. VYSE, best rate of climb with one engine inoperative. VMC, under 14 CFR Part 23, this is the calibrated airspeed at which, following a sudden critical loss of thrust, it is possible to maintain control of the airplane. Simply put, the minimum airspeed at which the pilot can maintain directional control after an engine becomes inoperative. More on this later. VSSE, the minimum safe speed to intentionally turn off the critical engine in flight. Accelerate stop distance, the total ground distance it takes for a multi-engine to accelerate to rotation speed, experience an engine failure, and come to a stop. Accelerate go distance is the horizontal distance required to continue the takeoff and climb to 50 feet above ground level, assuming an engine failure occurs at rotation as specified by the manufacturer. Absolute ceiling, the altitude where a climb is no longer possible with both engines operating at full power. Single engine absolute ceiling, the altitude where climb is no longer possible with one engine operating at full power and one engine's propeller feathered. Service ceiling, the highest altitude at which the airplane can maintain a steady rate of climb of 100 feet per minute with both engines operating at full power. Single engine service ceiling, the highest altitude at which the airplane can maintain a steady rate of climb of 50 feet per minute with one engine operating at full power and one engine's propeller feathered. The airspeed instruments on most multi-engine airplanes have markings that aren't on the single-engine airplanes to indicate some of these important speeds. There are two red radial bands. One is the never exceed speed, and the other is the published VMC speed. There is also a blue radial band, which indicates VYSE. So, what happens when the engine fails? When an engine fails in a single-engine airplane, the airplane simply operates like a glider in the sense that there is no longer thrust produced to oppose drag. In a multi-engine, however, when one engine fails, the other engine still operates, and this creates asymmetric thrust. Asymmetric means something is uneven or has parts or aspects that are not equal or equivalent. So, in this case, when the thrust produced by both engines is uneven, we say that it is asymmetric. Because the thrust is uneven, the aircraft will yaw towards the engine with the lower amount of thrust. This yaw occurs about the center of gravity and can be of varying magnitude. We call this yaw moment. Remember, moment is force multiplied by distance. Therefore, when there is a larger asymmetry in thrust, there will be a larger yaw moment toward the inoperative engine. In addition to the plane yawing, the imbalance of airflow generated by the propellers will cause the plane to roll towards the inoperative engine. Simply put, the airplane yaws and rolls in the direction of the inoperative engine. The magnitude of yaw and roll is dependent on the amount of asymmetry in the thrust the aircraft has. An aircraft with 90% power on one engine and 30% power on the malfunctioning engine will yaw and roll less compared to an aircraft with 90% on one engine and 0% on the inoperative engine. The first aircraft has an asymmetric thrust of 60%, and the latter has an asymmetric thrust of 90%. As a multi-engine pilot, you will be responsible for maintaining positive airplane control with these asymmetric forces when one of the engines fails. With a good understanding of these forces, as well as proper training, you will be able to accomplish this safely. Critical engine. Another important concept to learn is the critical engine. This term is used frequently when discussing one-engine inoperative conditions in a multi-engine airplane. In certain multi-engine airplanes, the intensity of yaw and roll produced when a particular engine fails might be different than when the opposite engine fails. This is especially true in multi-engines with conventional rotating propellers. In multi-engines with counter-rotating propellers, the aircraft reacts the same regardless of which engine has failed. The engine that produces the largest moment of yaw and roll when it is made inoperative or fails is the critical engine. Recall that moment is force multiplied by arm or distance. So, if there is a propeller with a longer arm, it will cause more yaw towards the inoperative engine compared to a propeller with a shorter arm. Also, a propeller producing more thrust will cause more yaw. So, you may be wondering why critical engines exist. Well, before we can talk about the factors that can help explain this phenomenon, let us review some propeller theories. Thrust. Propellers produce thrust, and in most airplanes, this acts parallel to the longitudinal axis. The amount of thrust produced depends on several factors, some of which include propeller angle of attack and revolutions per minute. The higher the angle of attack of the propeller and revolutions per minute, the more thrust. Prop wash. As the propeller produces thrust forward, it essentially pulls the aircraft forward. As it does this, it pushes air backwards. This air pushed backwards is what is called prop wash. If a pilot increases thrust, the propeller bites more air, and as a result, pushes that air backwards. In simpler terms, a propeller creating more thrust creates more prop wash. Torque. Torque also plays a factor. Torque is based off of Newton's third law. Every action causes an equal but opposite reaction. As a propeller turns in one direction, there is an equal but opposite reaction in the opposite direction. Conventional versus counter-rotating propeller installations. Earlier, we had discussed conventional and counter-rotating propeller installations. Conventional propeller installations have both engine propellers rotating clockwise from the pilot's seat looking forward. This is the same direction the propeller rotates in the Cessna 172. Counter-rotating propellers, on the other hand, have the propeller spinning in the opposite direction. One propeller rotates clockwise and the other counterclockwise. This design minimizes the effect of torque and other turning tendencies. P-factor. The other element that helps determine a critical engine is P-factor. P-factor is based on the concept that the descending blade of a conventional rotating propeller causes more thrust than the ascending blade. This happens because the descending blade has a higher angle of attack than the ascending blade when the aircraft is in a high-pitch attitude. This difference in angle of attack creates more thrust on the descending propeller than the ascending propeller. So, to review, conventional propeller installations on multi-engine aircraft have propellers on both engines spinning clockwise. The descending propeller on both engines are on the right, looking forward. Now, the descending propeller for the right engine has a longer arm from the center of gravity of the aircraft compared to the descending propeller of the left engine. The Diamond 42 is an example of an airplane with conventional propeller installation. In this situation, when the left engine fails, the arm of the descending blade on the right engine is longer than that of the left engine. Remember, the longer the arm, the greater the yawing moment that engine will produce. This leads us to understand that in our Diamond 42, the left engine is critical. This is because when that engine fails, the arm of the descending blade on the right engine is larger and so will produce more of a yawing moment. In contrast, if the right engine were to fail, the arm of the descending blade to the center of gravity is much shorter. This will result in a lesser yawing moment. In other words, if the left engine failed on the Diamond 42, the aircraft would have a larger yawing moment than if the right engine failed. Accelerated slipstream. There is also a phenomenon called accelerated slipstream. When air is accelerated over an airfoil, it increases lift. Propellers installed on wings of multi-engine aircraft create prop wash over the wing. This prop wash creates more lift, also known as induced flow. Accelerated slipstream refers to the induced flow of air over the wing behind the engine, which creates lift. With one engine inoperative, there is more induced flow of air over the wing with the operating engine, and this further causes a roll towards the inoperative engine. Torque. We discussed the theory of torque before. In the Diamond 42, when the propellers rotate to the right, the aircraft tends to roll to the left due to Newton's third law. When an engine fails in a multi-engine aircraft, the aircraft will tend to roll to the inoperative engine.
Let's use the left engine as an example. If the left engine fails, the aircraft will want to roll to the left engine. Torque on the right engine will also cause the aircraft to roll to the left. Remember, this is due to the propeller spinning to the right. If the right engine failed, the aircraft would want to roll to the right. However, torque will try to roll the aircraft to the left. As we can see, losing the left engine would be critical because you would have significantly more roll effect than if we lost the right engine.
For counter-rotating propeller installations, there is no critical engine, since the effect of torque, P-factor, and accelerated slipstream are the same.
This was the case with the P-38 propeller design. This was a multi-engine aircraft built during World War II. Interestingly, the propellers rotated outwards.
For any pilot, losing an engine during flight presents a unique set of complex challenges and requires prompt and correct responses. In a multi-engine airplane, regardless of which engine fails, a pilot needs to be properly trained to maintain positive aircraft control.